ELEC2 2019 question 4. A shop owner wants a buzzer to sound every time someone opens the shop door. One way to achieve this is to drive the buzzer from a NOT gate, which is triggered by an input subsystem consisting of an RC network and a switch S1 attached to the shop door frame. Part A. The RC network uses a 120 microfarad capacitor and a 36 kilo ohm resistor. When the switch contacts close, the capacitor charges up immediately to 12 volts. Okay, so we have a circuit diagram. Now we're told that when the switch closes, VC charges up to 12 volts. But what we're not told is what happens then when the switch opens. And what we need to realize is that capacitor, which is now fully charged, discharges, and what it does to discharge is it discharges through the 36 kilo ohm resistor, slowly dropping its voltage as it discharges. So for part 1, calculate the time constant of the RC network. Well, this is one of the easier equations to find, and hopefully you know it, and the time constant is T is equal to RC. We're just going to substitute in the values from the circuit diagram. So we have 36,000 and we have 120 times 10 to the minus 6. And that gives us a time constant which is 4.32, and we've got to remember the units, and that's in seconds. Okay, part 2. Switch S is momentarily closed and then opened at time t equals 0. Determine the time taken for VC to reach 6 volts. Well, we know that the supply rail is 12 volts and that the capacitor is charged to 12 volts. We're asking, or the question's asking, how long does it take to go from 12 volts to 6 volts? And hopefully you'll be aware that this is the half-life. Now the half-life equation isn't on the equation sheet, but hopefully you know what the equation is, and there's a couple of variations on the theme as far as this equation is concerned. T to the half equals RC ln 2 if you're a physicist, or maybe easier to remember is T to the half is 0.69 RC. So all we need to do is plug in the values. So this is 0.69 times 36,000 times 120 times 10 to the minus 6, and that gives us a value of 2.99 seconds, so approximately 3 seconds. Right. So B part 1. When the shop door is closed, the switch contacts are open. When the door opens, the contacts close. The NOT gate has a switching threshold of 6 volts. Complete the circuit diagram by adding the NOT gate and the buzzer. Okay, so we've got our circuit diagram. We need to add a NOT gate and a buzzer. Now the NOT gate's the easy bit, so all we're going to do is just attach it there. Don't forget the little circle on the end. But it's the buzzer. Now, what we need to remember is that we want the buzzer to go off and if we read the question again, it says complete the circuit diagram. When the door opens, the contacts close. All right, so we know that we've got 12 volts when the door opens because the contacts close and the 120 microfarad capacitor completely charges, which means we've got a high on the left-hand side of the NOT gate, which means we've got a low on the right-hand side on its output, which means as far as the buzzer is concerned, if we want it to buzz when the shop door is open, we're going to have to attach the buzzer up here. We just need to make sure that we know the circuit diagram for a buzzer, but it's got to go to the high volt rail, not your natural instinct is probably to attach it to the low volt rail. Okay, part 2. It says the shop door opens for 5 seconds and then closes. For how long does the buzzer sound? Explain your answer. Well, this was the most poorly answered part of this question, and this is actually in two parts. We know from the circuit diagram above that when the shop door opens, so that the switch is closed, that the buzzer will sound, and we're told it sounds for 5 seconds. We know that when the shop door is open, we're going to get 5 seconds worth of buzzer sounding. But when it's closed, we now need to think about what happens. So when the switch opens, the capacitor is going to discharge slowly through the 36 kilo ohm resistor. Now that means that the voltage on the input of the NOT gate is going to slowly drop from 12 volts downwards. Now we're told that the switching value for the NOT gate is 6 volts. So that's when it's going to register high differences between highs and lows. So how long does it take for the voltage to drop from that 12 volts that initially was down to 6 volts? Well, we've done that calculation already. So the time for closed is 3 seconds, because that was the half-life. So the total time that the buzzer is going to sound is going to be that 5 plus 3 seconds. So it's going to be 8 seconds. Okay, part C. So C part 1 is, after using the system for a while, the shop owner decides it would be more desirable to pulse the buzzer rather than have it sound continuously. The circuit is modified accordingly using the A-stable circuit shown below. For part 1, calculate the frequency and mark space ratio of this A-stable. So we've got the picture of the A-stable, but we need to figure out these two equations. Now, you're obviously aware that the data sheet doesn't have any names on it, so you've got to be able to recognize these particular equations. Now the frequency one is this one down the bottom here, whereas the mark space ratio one is the one at the very bottom of, I think it's the third sheet in the third paper in the data sheet. So these are the two equations that we're going to need to use. Okay, so for frequency, so we know that frequency is equal to, let me just get rid of that, 1.44 over R1 plus 2R2 in brackets times C. Now all we need to remember is which one's R1 and which one's R2 in order to get the correct values in here. Well, we're lucky as far as this question is concerned. Both of them are 12k, so we're going to have 1.44 divided by 12,000 plus 2 times 12,000, all in brackets, times 120 times 10 to the minus 6, so we can extend that. And what that does is it gives us an answer of 0.3 hertz. And that's quite a nice value, and hopefully you can recognize that 0.33, if you turn that into time, would be 3 seconds for a period. Right, mark space ratio. Now again, pretty straightforward. We know that time on over time off is going to be R1 plus R2 over R1, in fact, so R2, and that's going to be 12,000 plus 12,000 over 12,000. That gives us an answer of 2. Now, that in itself isn't a ratio, and the actual question does ask what is the mark space ratio. So therefore we need to give it in terms of a ratio. So the mark space ratio is 2 to 1. Now the final part of this question is using the axis provided, sketch a graph to show 2 cycles of the output signal produced by this A stable, given that it pulses between 12 volts and 0 volt. So we've got our graph. Now we know that the frequency is 0.33 Hertz, and therefore that gives us a time period of 3 seconds, or 1 divided by 0.33, which gives us 3 seconds. So we've got to incorporate that. So each cycle of highs and lows takes 3 seconds. But we know that the mark-space ratio is 2 to 1. So if the mark takes 2 seconds and the space takes 1 second. And we know that it goes between 12 volts and 0 volts. Now, you might ask the question, do we start at 0 volts for the space, or do we start at 12 volts for the mark? As far as the mark scheme's concerned, they don't care which one you use. You've just got to make sure that it's consistent. So I'm going to start with the 12 volts, so the mark, and this will go for 2 seconds. And then we're going to go down and go across for 1 second, up again for 2 seconds, and down for 1 second. And that concludes question 4.